Sir, good morning, sir.
Good morning, madam.
Good morning, sir.
Yeah, good
Sir,
morning, ma'am.
uh, shall we start now, sir?
Yeah, I'm ready, ma'am.
Okay, sir. MC girls, start now.
Things go back to normal when we create a new normal, and that's okay.
Good morning, everyone. Here's a hearty welcome, big and warm enough to encompass you all.
The things you're praying and hoping for tend to arrive at the most unexpected moments. Let us all open up our hearts to listen to the hymn of God.
There shall be showers of blessings. This is the promise of love. There shall be seasons refreshing, sent from the Savior above. Showers of blessing, showers of blessing we need. Mercy drops round us are falling, but for the showers we plead. Showers of blessing, showers of blessing we need. Mercy drops round us are falling, but for the showers we plead. There shall be showers of blessing, send them upon us, O Lord. Grant to us now a refreshing, come and now honor thy word. Showers of blessing, showers of blessing we need. Mercy drops round us are falling, but for the showers we plead. Showers of blessing, showers of blessing we need. Mercy drops round us are falling, but for the showers we plead.
Thank you for making us feel the presence of God.
Let's scout into the technical session. Here we have Dr. Selvarani, Assistant Professor, PG in Research Department of Mathematics, Holy Cross College, to take over the session.
Every day is a good day, and there is something to learn, care, and celebrate. A very pleasant morning to everyone present here. I take immense pleasure in welcoming you all for this second day international seminar. Every day is a good day, and that something to learn, care, and celebrate. A very pleasant morning to everyone present here. I take immense pleasure in welcoming you all for this second day international seminar on present trends in application of mathematics. I offer a grand welcome to the resource person of today's session. Every day
Silverani.
is a good day, and
Silverani.
there is something to learn, care, and celebrate. A very pleasant morning to everyone present here. Ma'am? Ma'am?
அந்த ஸ்டூடெண்ட்
Ma'am, good morning,
பேசுறது
ma'am.
அந்த சிஸ்டத்துல
Am I
பேசுங்க
audible,
நீங்க.
ma'am?
அதுல பேசுங்க. உங்க வாய்ஸ் பிரேக் ஆகுது முன்னாடி. இப்ப ஸ்டூடெண்டோடதுல பேசுங்க வந்து.
Okay.
ஸ்டூடெண்ட் எம்சி பண்றாங்கல்ல அதுல வாங்கி பேசுங்க அந்த லேப்டாப்ல.
Okay, ma'am. Okay, ma'am. Okay. Every day is a good day, and there is something to learn, care, and celebrate. A very pleasant morning to everyone present here. I take immense pleasure in welcoming you all for this second day international seminar on present trends in application of mathematics. I offer a grand welcome to the resource person of today's session, Dr. Rajendran Swamidurai, Professor and Coordinator of Computer Science, Alabama State University, United States of America. Sir has received his PhD in Computer Science and Software Engineering from Auburn University, USA. Sir is also an IEEE senior member and has received the prestigious US Department of Defense Summer Faculty Fellowship 2 times in the consecutive years 2018 and 19. His research areas are software engineering and big data analytics. The US National Science Foundation has awarded him 4 research grants totaling $1.2 million for his research projects. It is indeed a great pleasure in welcoming you, sir. Now I hand over the session to Dr. Rajendran Swamidurai on the topic of mathematics for big data analytics. Sir, kindly take over the session.
Yeah, thanks a lot for the very kind introduction. I like to thank Dr. Rita and other committee members there. So I'm just recalling my past. Actually, we are colleagues 20 years back, I think 1996. So after a long time, I'm meeting. So thanks a lot for every one of you. Okay. So let me check it. Maybe I need your help to. Okay. Screen.
Yes, sir.
Yeah.
You present, sir. I will tell you whether it is visible. Present your screen, sir.
Yes, ma'am. Just now I opened it. Is it visible, ma'am?
Yes, sir. Yes, sir. It is visible, sir. It is clearly visible. Your voice is also clear, sir. You may proceed,
Okay,
sir.
ma'am. Okay, thanks
sir.
a lot, ma'am. Thank you.
Thank you, sir. Thank you.
Okay, my name is Rajendran Swamidurai. You can just call me Raj. And I'm also from Trichy. So happy to So actually, I studied just across campus from Kodikras in the Bishopur Higher Secondary School, actually in my high school. Okay, thanks a lot for this opportunity. So big data, so I don't want to bore you with what is big data and what are the definitions and other things, but I want to focus on certain key important points. What are the big data opportunities available here, and with mathematics, what we can do with the big data, those kind of things. So first thing is, what we have to understand is the digital universe or the big data, it is doubling every 2 years. So because we know that nowadays we are doing everything online. For example, even this meeting and this presentation. So nowadays our class, our work, our private life, our banking, business, education, everything is, we are doing it in online. So the data, the digital universe is growing very fast. This is actually before this pandemic, doubling 2 years. Maybe nowadays it may be more than that. And not only the online or our online job and the smart devices, we are having almost all the smart devices, starting from our cell phone to our washing machine to our cooking range, our car. All the devices are nowadays smart devices. Every device is transmitting data and receiving data. So that also contributing a lot for the digital universe. In 2019 alone, there were 4 billion people were in online. That's in 2019, before the pandemic hit. Now you know that almost everybody is in online now. And millions and millions of enterprises are becoming more and more web-based now. So all the sales here nowadays, everything is online sales. So almost all the stores are closed, everything online. And not only the enterprises, there are millions of sensors, street cameras to other communicating devices. A lot of sensors is planted everywhere in the buildings as well as roads and all the infrastructure. So that also contributing for our growth of data. And last year alone, there were 10 billion mobile devices in use. Imagine then each cell phone, how much data it will generate. So what they're predicting is around now almost we are having 40 zettabyte of data currently available, stored now. But they are predicting that within 5 years, it will become 165 zettabytes of data. Then imagine how fast the data is growing now. So already we talked a lot of things about the data growth, but the exponential growth is contributed by a lot of applications and other things. For example, in last year alone, there are 2.3 billion active Facebook users. And the Facebook alone handled 30 petabytes of data. And the Twitter users, almost they are sending 500,000 tweets per minute. Same 1 billion Google searches for every day. And Walmart, actually the largest retail company in US here, they're storing almost 4 petabyte of data per day, their sales transaction alone. Then the Netflix movie, they are streaming almost 1 billion hours of TV shows per month. And YouTube, we are almost uploading 5 hours of video per second. So every second, 5 hours of video is uploaded to the YouTube. And not only these user devices, even a lot of telescopes and other scientific devices also contributing for this exponential growth. That is already hidden. Many people, we don't know that we are thinking only in terms of internet and other sensor devices and other things. But a lot of modern telescopes, which is studying the space or other things, that also contributing huge amount of data growth. So the data is growing exponentially. So this is the summary of that, just one day, how much data different applications are generating. And as a mathematicians or as a software engineer, for us, this data growth, it is not a trouble for us. Actually, only for the data warehousing people or data mining people, that will be a headache. Because once I worked as a database administrator, DBA, so once the data growth, we will get tensed up because our job will be very tedious, will become tedious. But as a mathematician, for you people, it's a great opportunity. So the doors are opened now actually because of the big data. So there is a new kind of data analytics is there. It's called the big data analytics. Already you know that there are plenty of job opportunities are opening. So we have to see this as a door opening or a great opportunity for mathematicians. Previously, mathematics means it's normally mostly normal traditional jobs will be there, teaching jobs or some banking jobs, those kind of jobs. But nowadays, the sky is the only limit. So only you need imagination, some kind of creative thinking, then you can go to any place. Now mathematics mathematicians are highly in demand, and even for example, you take people like me. I am a software engineer, but I'm doing a lot of mathematics. I studied a lot of mathematics, and I am using a lot of mathematics for almost for last 10-15 years. So we are living with mathematics. So without mathematics nowadays, nothing is there. So there is a big door opening is there for us. For example, in 2012, only 23% of organizations had the big data strategy. But now almost 97% of the organizations are investing money on big data. That means they are going to hire new people, new infrastructures and everything. There are new opportunities for mathematicians. And our Harvard Business Review also indicated that almost 70% of the Fortune 500 companies are hiring data scientists. And this is here US Bureau of Labor Statistics. That's a government organization. It will project the job on the government sector. That itself projects that there are 34% job increase in US government alone for the big data analytics. So that will be the proportion. It will be in the Europe as well as in India and other countries also. Then another the leading statistics organization, McKinsey Global Institute, also reports that there are 50 to 60% of more data analytic job is going to be created in the near future. So in 2010, the Forbes reports indicate that there are 2.7 million data scientists and analytic jobs opening. So this is mainly in US alone. Then imagine the other places and Europe and other places. So there are huge opportunities for the big data analytics. See, many people, they will get confused with the data science and big data. Big data is, maybe it's part of data science. Both are totally different things, altogether different animals. But you can do you can use the data science for the data analytics, big data analytics or normal data analytics. But both are totally different things. Dealing with a huge amount of data here, we are talking about petabyte, zettabyte of data. Okay. So let us talk about my own personal experience on the big data. So this is, you see, in 2014 itself, actually in 2012, I envisioned that the big data is going to become a big boom. Then at the time, I wrote a proposal to the National Science Foundation. Here, that's what our top science institute here, the National Science Foundation. So they are the one who is funding for all the research project. Almost all the US research science related project is funded by the National Science Foundation. And so I wrote a grant in 2014, and immediately they offered me a 400,000, almost 3 crores Indian rupees only for this big data, just infusing the big data in undergraduate mathematics curriculum. We are not going to do anything grand. You see, because they understood the value at the time itself, 2014 itself, they given the money. So, and we are almost infusing the big data in almost in all mathematics courses here, last 4 to 5 years now. So we are successfully running, and be able to train a lot of our mathematics students into big data, and they got very good jobs. They are doing pretty well now. So actually in the big data and mathematics means, so these are these are in the order actually. So the linear algebra is the most widely used mathematics concept in big data. Suppose you are good in linear algebra, then you are having bright future in big data. So linear algebra is the main thing, along with the matrix. Okay, linear algebra and matrix algorithms, matrix operations, those kind of things, that's a main thing. Then the discrete mathematics comes next, then differential equations, partial differential equations, probability and statistics. I don't want to separate probability and statistics because we are using together in the analytics field. That's why we are saying probability and statistics together. So if the data is numerical data, then normally we will use statistics. If it is categorical data, then we will use a probability. Already you know that. I no need to tell because you are a mathematician. You are mathematicians. I am just a software engineer, but I am using mathematics, so that's why I want to put it together. Then the modern geometry. The modern geometry is picking up now. That's many people are predicting that the modern geometry is going to be the future of the big data. So it's going to have a lot of job applications in the big data area. So let us discuss one by one in little more detail. Okay. So linear algebra and big data. So there are a lot of linear algebra topics widely used in big data, starting from your linear equations, eigenvalue problems, principal compound analysis, just you name it, from optimization problem, everything, almost all the linear algebra is used in practical applications. Let us see one by one later. But please understand that linear algebra is the backbone of almost our big data analytics. So already I told you that linear algebra, so the matrix algorithm along with your things. So that's a main thing. That's a core. So most of the things we are trying to convert everything in matrix. Then we are processing the matrix for the big data analytics majority of the times. So for example, actually, most of your big data analytics is nothing but manipulation of large matrices. Large matrices means we know that we will do the multiplication of two matrices, two square matrices. But here we are talking about multiplications of 100 matrices or 200 matrices, because the dimensions, if you talk about your data, then each and every characteristics will be represented as one dimension. So that will become one matrix. Then imagine multiplying matrix A and B is easy. But what about multiplying matrix A and B and C? Like that, if you multiply matrices A1, A2, up to A100 or A50, imagine 50 matrices multiplying the same time. It's practically manually, we cannot do that. So that's what we are talking about the big data here. Not just multiplying two matrices or three matrices, multiplying huge amount of matrices. So like that. Not only just for example, I'm telling matrices, but any matrix operations involves huge amount of large amount of matrices and huge amount of matrices. And for example, the Google's page rank method, its eigenvector concept is widely used in the Google page rank. But for example, if you are interested, this is the rank actually how they are calculating. If you click the Google Wikipedia here, you can find out how the page rank is working, how the eigenvectors is used there. You'll get a lot of information about that. Okay, so this is the right hand here. The diagram is the one example of the page ranking. So what they will do is they will use the matrix multiplication and they will assign the parameters. Then they will calculate the ranking of each website. Then finally, which is having the higher higher value, that will be ranked higher top. Then the second ranking. That's why once you having a searching or anything, you'll get the top 2, 3 like this. So you can go to the page rank, you can find out, you can see it's all matrix operations. You can find out a lot of, you see here, it's all matrix operations. It's all eigenvalues, eigenvectors. So it's all matrix operations. So you can find out a lot of information about this. Okay. And now let us see one by one. For same linear algebra, not only we are using for Google rank, these are some of the examples of the linear algebra in the big data practical applications. Already we talked about the Google's page rank and recommender system. For example, you are logging into a Netflix or any other movie site, automatically it will give you some suggestion, or even the YouTube. If you open it, it will give some suggestion for you. These are all the recommender systems. Those are even if you open your web page, if you search something immediately, next time, if you see, there are a lot of advertisements will come for you, depending upon related to the search. So all these recommender systems all using linear algebra. And the topic modeling, like your Wikipedia and other concepts are using, again, linear algebra. And your network analysis, your Facebook analysis or your YouTube analysis, all these things also using. And internet searching, your image segmentation, graph clustering, almost a lot of applications uses linear algebra. So let us take one by one now. So linear equations and matrices in the linear algebra concept. If you take only linear equations and matrices, it's having three major applications. One is the large network analysis. The huge network is analysis used linear equations and matrices. Then length of economic model. So this is the model, actually the demand and supply model. So this model also uses your linear equations. And ranking the sports team. Rank 1, 2, 3, 4, all these are done by your linear equations and matrices. So these are the practical applications. So we mathematicians, we know all these basic concepts. The idea is once you try to mix this one with the practical application, then there is a lot of future is there. Then next is eigenvalues and eigenvectors. If you take only eigenvalues and eigenvectors, it's having a lot of application. Again, the page rank is already we talked about. Then clustering the network. So network grouping of the networks, that means the clustering concept, and the weather modeling, weather forecasting or cyclone forecasting, heat, rain forecasting, all these things, systems are uses your eigenvalues and eigenvectors. And the link predictions, who is liking what. So these kind of link predictions also uses this. And then again the spectral clustering. You see this, there is the elephant picture. That's a spectral clustering. That means how to cluster various parts in the image. So to identify the various parts of the image, they are using the spectral clustering. And like this, there are plenty of applications are there in eigenvalues and eigenvectors. These are the practical real world applications we are using day by day. So even for this spectral clustering, this image processing, we are using widely in our many of our military projects and other things. Actually, even myself, I involved in a couple of projects there. Then your principal component analysis and the single value decomposition techniques. These are used mainly in the comparing the protein structures, how the proteins are folding, whether two proteins, how it's folding, whether to compare two different folding structures. They are using in the DNA sequence and protein sequence, all this sequence, they are using your PCA as well as singular value decomposition techniques, as well as the image compression technique. For example, you have a huge file. You have for example, here we have 8.9 MB file. If you want to reduce the size of the file, the image compression also uses these techniques, your linear algebra technique. Then L nano. This is your weather pattern prediction, how the cyclone is moving, how the warm air is moving, all this prediction. This is called L nano. So these techniques you may see in the weather channels most of the times. So this prediction is done using PC and SVD techniques. So again, it's a linear algebra. And optimization and linear programming is widely used in the stable marriage problem, production planning, transportation problems, minimizing cost, minimizing environmental damage. All these practical applications uses optimization and linear programming concepts of your linear algebra. And similar items and frequent pattern concepts also uses on face recognition, fingerprint recognition. Nowadays, you know that most of you are using the iPhone. So it's having that fingerprint thing or recognition. All these things are done using linear algebra. And your Netflix movie rating, all this concept, even the plagiarism finding, whether your paper is copied from some other paper or not, all these things are done in the linear algebra. So all these applications are linear algebra. So if you can see that linear algebra playing a vast role in big data analytics. So you want to become a good big data analytics person, then you have to go back and thoroughly understand linear algebra. So that's my personal suggestion. Then next is discrete mathematics. Actually, you know that the linked information is represented in terms of a graph, vertices and edges, or nodes and edges. So mostly the graph representation. So all your, even for example, your World Wide Web, that's nothing but a large graph. So in terms of the computer, the World Wide Web is nothing but it's a graph. And your page rank and other concepts are, it's nothing but how strongly the graphs or nodes are connected to each other. And the internet advertising, so already I mentioned you that if you search something in Google today, if you type something on car, next day you can find a lot of advertisement on your search engine. So that's all uses the bipartite graphs actually. So this all you see here, the advertisements and your based upon your searching habits and other things, they will give the advertisements, a lot of advertisement to you. That's all bipartite graphs. So the graph theory is discrete mathematics. That means in the internet, the graph theory, it's used a lot actually. Again in big data analytics. These are some of the application examples. And this one is the another example is, for example, you are how popular you are among the people or in the social media, or who is influencing the market. Those kind of analysis can be done using your graph theory. This one, discrete mathematics and graph theory. For example, you want to find out the election result, who will win, and or who is popular among the people, or popular among a particular group of people, who is the leader in the particular field. Those kind of analysis you can do this using discrete mathematics. So these are some of the example related. All these you can use this for any related examples in any application area. You can use it for agriculture to find out the crops or the disease, or even the healthcare system. Only thing is, these are some of the examples you can apply this into any application area of your interest. Next is differential equations. So many of you heard that spatial data analytics or spatio-temporal data analytics. Spatial means the places. So how a particular event is happening in different places. So the map, so that's a spatial analysis. Spatio-temporal means time. So for example, your gas price or petrol price or your gold price, how it changes over time, how the stock market is changes over time. That's called temporal analytics. Spatio-temporal means both with respect to time, how the particular space, for example, you take Tiruchirappalli, how a particular region is growing in Trichy, a particular Tilanagar or some areas, how it's growing throughout the years. So that kind of analysis, or how the forest is shrinking, or how the temperature is keep on changing, or how the traffic near your college, how the traffic is increasing on particular time. Sometimes it will be more in morning, afternoon it will be less. So those kind of analytics, it's called spatio-temporal analytics. So all these things are using differential equation as well as partial differential equation. Even your disease modeling. So how the virus is spread or where the virus is spreading, all these things, and image visualization. A lot of concepts uses differential equation as well as partial differential equations. So this is one of the example of the disease modeling actually for the differential equations. So all this is the example of the spatio-temporal. So how these particular things are happening in particular places. This all model using differential and partial differential equations. So all this spatial mapping. Okay. Next is already I told you that probability and statistics also we are using in big data analytics. So for example, your computational statistics method, your Markov transition matrix or Bombronic principles or Monte Carlo simulation, they are widely used in a lot of especially the Monte Carlo simulation, it's widely used in a lot of big data analytics applications. Similarly, probability. So already I mentioned you that if your data is numerical, then it's fine. We can do any distance formula or anything to calculate certain things. But your data is it's a categorical data. For example, people will the liking if they put 5, 4, 3, 2 like that, the rating for something, we can do mathematical calculations. Suppose if they say very good, good, excellent, like that, then how we will do the calculations? So then we need to use the probability concepts. So a lot of probability concepts are widely used, especially the Bayesian and the Navy Bayes. Those kind of techniques are widely used. That's why I highlighted there. And Markov chain, Monte Carlo methods, and the Gibbs distribution. A lot of probability distributions are widely used in almost in all big data analytics. So statistics means generally numerical data. Probability means categorical data. That's what normally we will go for the analytics point of view. So the statistics and the probability, the practical applications, your market segmentation. So how the market is how segmented, what kind of area people using which item, those kind of things. Then customer churn. Customer churn is nothing but retaining the student. For example, the universities also how to retain your students. If they're once they come inside, how to retain. Some people they may leave your school or your organization. How to avoid that. Those kind of analysis is done through your big data, that kind of big data analytics based upon their. For example, here we have a system that it will warn the faculty members the students are at risk. For example, some students are not using. We are using a software Blackboard. So if people are not accessing my course frequently, assume that two students are not accessing my classes frequently. They are accessing weekly once or 2 weeks once like that, and they are not submitting assignment on time and those kind of things. Then immediately this analysis algorithm will warn me. Actually, I will get a text message or an email message saying that this person is at risk of failing in your class. So then we will inform to our management or their parents or guardians or even to the students. I will call the students and I will talk to them. What is the problem with you? What's going on? How we can make sure that you will pass in my course, those kind of analysis. So that's what the customer churn. So a lot of practical applications are there. And fraud detection, direct marketing, interactive marketing, all these concepts, we are using a lot of statistics and probability in big data applications. My personal suggestion is, for example, how to do customer churn in big data analytics. Then you will get a lot of literature, then learn from that. So every small item, every bulleted item is having a research component in it or job component in it. So once you start exploring any one of these item, then you will become a good big data scientist or a data scientist in the future. And modern geometry. So this is the new things happening in the big data analytics. So mostly what they're doing is the high dimensional data. For example, already I mentioned that the data is, I stored information about a person, 20 information. So 20 information means it's a 20 dimension. That means 20 dimensional matrix. So then I have to store it in a tensor, which is having a rank of 20. Then if I want to multiply that, imagine if I want to multiply a 20 dimensional matrix with another 20 dimensional matrix. Then it's very, very huge task. Sometimes it's impossible for the computer to do it. So for that, what they're doing is they're using a lot of geometry concepts to reconstruct that high dimensional space into low dimension. Instead of 20 dimension, they will convert into 10 dimension or 5 dimension or 2 dimension or even linear or vectors. Then after that, processing is easy once you convert into low dimensions. Even some people, what they're using triangle and other concepts to segregate that data. Then from that, only within that triangle, they will do some kind of operation. So the graph is used in modern geometry. Modern geometry is used in a lot of things. Even reconstruction of, actually, for example, they used to say that there is a famous project called reconstruction of Rome. Meaning is from the old picture, they will reconstruct the city. So like that, suppose you want to reconstruct a building, it's demolished or something, or you have some item that is, you lost it, but you have the picture of that various pictures. Then from a particular point, I am sitting in this, then that picture is, if it is taken 45-degree angle, then we can reconstruct the 3-dimensional image from the 2-dimensional. That also used modern geometry. So that again, it's having a lot of applications. This is a growing area of big data now, the modern geometry. So just I want to say something here. Already you are mathematicians and you may doing a lot of data science and other things. So we are learning the theories. And once you start learning some of the tools, the big data tools, then you start learning any one of the big data analytics area, for example, linear algebra or your geometry or any one of the area, translate and learn some big data tools, then you will become a good data scientist. So you have a lot of bright future. Already I mentioned in my starting slides, there are so many job opportunities are available everywhere in the world for the big data analytics or even data scientists. So there are so many job opportunities are available. So almost now in US, almost all companies are hiring data scientists. In same thing, it's happening everywhere, and all the applications are done in through data science. So everything is mathematics. So that's what I'm coming to say. We are use a lot of mathematics, and even if you take only one particular mathematics, I can talk big. Actually, we are doing real big projects, so we can talk hours together or days together in one particular topic. For example, you take eigenvector, eigenvalues, then we can talk about days in big data analytics. That kind of opportunity is there. There are almost everything is based upon mathematics now. So you are in a good hand, actually, mathematics people. You are choosing the right path. Only thing is, if you learn some data analytics tools like Hadoop or other servers, other Python and other languages, then definitely that will help you a lot in going in your future. And before going to the question and answer session, please understand that I am not a mathematician. I am a software engineer. And so just if you have any questions, please ask me, then I will be happy to.
Dear participants, if you have any queries, kindly post your questions in the chat box.
Yeah, thank you. That will solve a lot of problems.
Dear participants, if you have any queries,
kindly post your questions in the chat box. Okay.
For statistics, mostly SAS is the main package, but the thing is, SAS is, you know, that it's very expensive.
Sir?
Yes, ma'am. Actually, somebody asked which is the best software for better for statistical computations. Actually, yeah, R code. No, there is, yeah, Python also. Yeah, Python is a general purpose. So you can, since you talked about statistics, just I mentioned SAS and R, and but Python is used for everything. But normal current data scientists normally they will mix R with Python. Sir, how a student can take step forward to get good job in analytics? No, that's what I'm saying. Actually, if you want to become a good analytics, then what you need to do is first thing is you have to be sound in mathematics. Okay, so you in all area of mathematics as well as statistics. So you must have basic, not necessarily you have to be a very expert, but you must have the basic sound knowledge in your mathematics as well as statistics concepts. And next thing is you need to learn some languages, either R or Python. That will help you a lot. And another thing is then you have to learn, if you are really interested in big data analytics, then you have to use Hadoop server or 1 minute. There is one more software, just a minute.
Sir,
Hadoop is one, then 1 minute. Hadoop is one, then TensorFlow. That's nowadays we are using a lot TensorFlow software, and Spark, Apache Spark. So Hadoop, Spark, and TensorFlow. So these are the tools you must any one of the tools will help you a lot to become a good data analytics.
So next question from Keshav Kumar. How a student can take step forward to get good job in analytics?
Yeah, that's what I'm talking now. Sorry, there is a thing. So
Okay, sir,
for the good
next
data
question,
analytics, yes, ma'am. For the good data analytics, that's what I'm mentioning. They have to be. Yeah, I think there is a lag here.
Okay, sir.
Yeah, please.
Yes, sir.
Yeah, please go ahead.
Next question from Gunashekaran Kalam. Tell me the role of graph theory in data analytics.
Okay, 1 minute. See, graph theory means everything is, you see, graph is what? It's a interconnection of networks, am I correct? Suppose you want to, for example, internet advertisement. So what it is doing is, it is connecting the people interest whenever you are doing some searching. So it is picking up some keywords from you, and it's trying to match the products. Already the product vendors, they may have their own product, so it will try to match you. So it's creating a graph. So yeah, most of the operations, mostly the advertisements on recommender systems and everything, what it is doing is it's trying to connect the customer as well as the supplier, and it's creating a network, and then it's providing the network service. So most of this, for UG math students, what software we need to teach. That's what actually math students normally we are using here, while we are using R.
Okay, sir.
The R is the popular one among teachers here. Yeah, thank you.
So difference between data science and big data analytics.
Again, yeah, already I think I mentioned it. The data science means the data size doesn't matter. So it can be a small data or big data. So data science means what you are doing is you are gathering the data, the input and output, then you are creating a model from the data. Then the model will tell you that any trend or any classification or those kind of things. So data science means just from the data, we are trying to generate a model. Then that's model building, and from the model building, we are doing whatever the analysis or whatever we want to do. That's a data science. Big data means it's dealing with a huge amount of data, not only huge amount, sometimes the huge dimensional data. For example, the data may be small, but it may have the more dimensions and other things. Either the size or the velocity or veracity, those kind of things will be more in the data. So that you cannot do normal data science applications. For example, you are doing let us take one example. You are clustering. You are doing for normal data science. You can use a k-mean clustering, a normal k-mean clustering. But big data analytics, you cannot use k-mean because the huge amount of data it will not support. So that's the difference. The size of the data, that's what the difference is.
Okay. Thank you, sir.
Yeah, thank you.
So there is no more questions, sir. Shall I conclude, sir?
Sir, Rita speaking, sir.
Yeah, hello, ma'am. Yeah, please.
Yes, ma'am.
I want to ask some questions, sir.
Yeah, please,
Sir,
ma'am.
Today, at present, we are in the process of finding the vaccine for the COVID-19. So in what way, but according to the expert analysis, it is given that the vaccine must be given to the patient for 3 rounds. That is round 1 and round 2, round 3 it's given. So now how far it is successful, that is obtained by taking the statistical data with respect to the physical condition of the patient as well as the effectiveness of the vaccine also. Then at this pandemic situation, how this data analysis will be useful for this situation, or vaccine processing, how it is useful for the vaccine processing?
You are saying that we cannot, why the pandemic is coming into play. That's what my question is here now. So why you add the word that in this pandemic time?
Sir, really it is the pandemic time, sir, because it is the virus, it's like a virus. So it is spreading more effectively. So we are all staying in the home. That's what we have a seminar in online. So as per the procedure of finding the vaccine, now they need some data analysis for this process. In order to validate the effectiveness of the vaccine, we need some data analysis. Like that only I read from the paper last week. So my question is, how far it is this data analysis useful for the vaccine to find the effectiveness of the vaccine? So far we have not yet decided. It is not finalized. It is not finalized for the vaccine.
Yes, doctor. Actually, yes, actually, data
analysis.
Actually, honestly speaking, especially this COVID situation is slightly tricky because most of the company, they don't want to give the data for analysis. Actually, that's a real situation because they don't want to. Every company, every scientist, those who are doing research, actually, they are not sharing it with anybody. Actually, so this situation definitely it's very difficult unless otherwise the data is become public. It is not become public due to many reasons. So now here also actually whatever they are giving, only they are doing it with the internal for that particular company. Only they are doing the data analytics. Actually, it's not available in public. So people are simply taking from some what can say unauthorized data or something. Then they're coming to some conclusion, but actually the data is not available. That's a thing now.
Yes, sir. Okay, sir. One more question, sir. Kesav Kumar, he raised one question, sir. Explain the principal component analysis.
No, already I mentioned I am not a mathematician. So I am only using, if you ask me this kind of direct mathematics question, I am not a mathematician. Please, you please ask your own professors there. Normally what we are doing, I am already told you that I am a software engineer. We are using only, we are only using the practical applications of these things. And that too not, we are not using all these components, whatever I mentioned here. For example, my current research is mostly on, we are using only the TensorFlow more and more. So TensorFlow and image processing applications. So we will use only few things. So that's the honest answer is, I cannot explain better than your mathematics teachers there.
Yes, sir. One more question, sir. In image processing, what are all the max concepts you are using?
Actually,
processing.
So normally what we do is, actually we are using many things. First thing is the dimensional reduction. Already I mentioned you that. So what we are doing is we are trying to take high dimensional, then we are reducing. Then another thing is what we are doing is we are converting image. We are taking a portion of image, then we are trying to convert that into bitmaps. From the bitmap, then what we'll do is it will give us a two-dimensional structure or matrix structure. Then we will convert that into vectors, linear vectors. Then we will process. So mostly we are using matrix operations, matrix and list processing, mostly matrix and list, and data frames. We used to call it in Python. So we will use some data frames. Then we will convert that into list of list. Then we will process it.
Okay, sir. Most of the participants are commented that your presentation is nice, and then the
Yeah.
explanation what you are given is very clear. I want to ask
Okay.
one more question, sir. It's my
Yeah,
personal
please.
question.
Mm.
Sir, can you tell me the job opportunity which is available for the big data analyst in America?
Almost here in every job, every company, every institution is having a opening for big data analytics. The real truth is they are not finding the right people. For example, in big universities here or research schools, for example, you take myself and my wife Uma, we are in the summer, we are working the 9 months in the universities. Then the summer we are going to the army research. Here we are having army research lab headquarters. That's the top research institute in the US actually. So in the summer we are going and 10 weeks we are doing research there actually. So because they are not getting the data science people, then they are hiring part-time people to do the jobs. So whether it's a student or so it's available everywhere. Only thing is how well you are ready, how you equipped you are. That's a question here now.
Okay, sir. What's the qualification they need for this particular job, sir?
No, that's what I already mentioned, that what they will expect is they will expect you to know the basics of mathematics and statistics. So how good you are in statistics and
Is there any
mathematics.
qualifying exams are available, sir?
No, there is no exams here.
How
No
to find out
exams.
that there is a vacancy there? How to find out? So is there any source to find out the vacancy there? Because many students, many PG students are well versed in data analytics, but one course is available in Coimbatore. That's an integrated course for 5 years for data analysis. Okay. So some students, they got a degree for this data analysis also. So can you tell me the sources in which they have to find out the job for their future?
Yeah, definitely. But I'm not having it right on my hand. But maybe I need to talk to some of my mathematics people here, because my focus is mainly actually since I'm in the computer science side of that. So what I will do is I have good contacts here. So maybe I will get talk to them and I'll get back through email.
Okay,
So that will
sir.
be the best thing. So
Okay, sir. Okay, sir. Thank you very much, sir. Thank you very much for your presentation.
yeah. Thanks a lot
Thank
for
you, sir. Now
inviting
I
me. And
hand over this to Selvarani, sir. She will continue. Thank you, sir. Thank you very
yeah,
much.
thanks a lot. And thank you. If there is anything, please email me. Thank you.
Okay, sir. Definitely.
Thank you.
Ma'am, shall I
Selvarani?
conclude, ma'am?
Yes.
Thank you, sir, for enlightening us on how each and every part of mathematics is applied in day-to-day life, especially how linear algebra is very much helpful in almost all real-life practical applications. Explained how World Wide Web is using the concept of graph theory. You made us to realize that both pure and applied mathematics are very helpful in almost all digital transaction and online transformation. Thank you, sir, for sharing your words of knowledge. Sir, you have enriched and nourished our minds through your thoughtful speech. A very big thanks to you, sir. Thank you.
Yeah, thanks a lot for inviting me. And
Thank you,
yeah,
sir, for accepting
thank you.
our
Yeah,
invitation. Thank
yeah.
you for spending your valuable time. I think now it is in the night, no, sir. Can I know
Yeah,
what's the time?
it's 11:35 now.
Thank you very much,
No,
sir, for
thanks a
sparing your
lot. So yeah, it's
valuable
not a
time.
problem. Yeah.
Okay, sir. Okay, thank you very
Thanks a
much,
lot.
sir.
If there anything we can, if anything is there, please send us for any
Definitely,
future
sir. I will
collaboration or
collect
anything.
your
We will do.
question, feedback from the participants. I will mail to you, sir. Thank you, sir.
Sure.
Thank you very much,
Yeah,
sir.
thanks a lot, man. Thank you, man. Thank you.
Outstanding people have one thing in common, an absolute sense of mission. Let's move on to the next session of this international seminar.
We now request Dr. Madeline Vinoda, Assistant Professor, PG and Research Department of Mathematics, Holy Cross College, to take up this session.
A very pleasant morning to each and every one of you for being here with us today. Welcome to the International Seminar on Present Trends in Applications of Mathematics. It is great to see all the enthusiastic participants are here to take part in the international seminar virtually. It is my pleasure to welcome and introduce the resource person of this session, Dr. Mary George, retired Associate Professor and Head, Department of Mathematics, Mar Ivanios College, Trivandrum. Madam has been coming from God's own country, Kerala. She has completed her MSc and MPhil in Mathematics from the University of Kerala. As correctly pointed out by the woman scientist, Stephanie Hawalk, all sorts of things can happen when you are open to new ideas and playing around with things. She is a proud recipient of first PhD in mathematics in the year 2002 from the Mahatma Gandhi University, Kerala, with the title Fuzzy Mathematical Approach to Economic Problems. Also, she is a recipient of Postdoctoral Research Award of UGC in the year 2004. She has been an approved research guide of University of Kerala and Mahatma Gandhi University and successfully produced 7 PhDs in mathematics from the University of Kerala. She has participated and presented several research articles in national and international conferences. Also, she has published several research articles in national and international journals. To add to her credit, she has authored several books in mathematics, mathematical economics, and ethics and value education. She has been a joint secretary of Kerala Mathematical Association. Also, she had been a chairperson for Board of Studies in Mathematics UG, University of Kerala from the year 2014 to 2017. We are indeed privileged to have such an eminent scholar amidst us today. Hearty welcome to you, Madam. I cordially welcome our dynamic head of the department, Dr. W. Rita, Assistant Professor, PG and Research Department of Mathematics, Holy Cross College, Trichy, to this session. I extend my warm welcome to all the faculty members and research scholars from the various parts of our country to this session. I hope this knowledge sharing session would bring you the new innovative ideas in the field of mathematics. Once again, I welcome you all. General instruction. Dear participants, kindly mute your video and audio throughout the session. You can post your queries in the chat box. Let us have a discussion at the end of this session. Now, I hand over this session to Dr. Mary George to share her views on the profound application of mathematics from counting to COVID-19 and beyond. Please, Madam.
Dear Principal, Reverend Sister Dr. Mussanah Rajeshwari, Dr. Rita, Head of the Department and the convener of the conference, all the members in the organizing committee, students, and all who are participating in this conference, my warm greetings from Bangalore. I sincerely appreciate the organizers of the conference for choosing a great and relevant topic for the conference, that is, present trends in applications of mathematics, because people in general about numbers and some operations on them, like addition, subtraction, multiplication, or division. Operations on them, like addition, subtraction, it is dear principal, I want sister Dr. Christina Bridget, Dr. Rita, head of the department and the convener of the conference, all the members in the organizing committee,
Dear Principal, Reverend Sister Dr. Christina Bridget, all the members in the organizing committee, students, and all who are participating in this conference, my warm greetings from Trivandrum. May I take this opportunity to thank all the organizers, especially Dr. Rita, my good friend, for inviting me to this conference. I sincerely appreciate the organizers of the conference for choosing a great and relevant topic for the conference, that is, present trends in applications of mathematics, because people in general and students of mathematics in particular are not aware of either the immensity or the splendid application possibilities of our subject mathematics. I think this is the last lecture in this conference. The topic on which I would like to talk is the profound applications of mathematics from counting to COVID-19 and beyond. First of all, let us think, what is mathematics? For a layman, it is all about numbers and some operations on them, like addition, subtraction, multiplication, or division. According to Galileo Galilei, the Italian astronomer, physicist, and engineer, who is rightly called as the father of modern science, mathematics is the language in which God has written the universe. He continues, philosophy is written in this grand book, the universe.
which stands continuously open to our gaze, but it cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It is written in the language of mathematics, and its characters are triangles, circles, and other geometrical figures without which it is humanly impossible to understand a single word of it. Dear friends, my talk is organized in this way. First, we will see a very brief account of the evolution of mathematics. Then, the applications of mathematics in general. Then, the applications of mathematics in the field of medicine. And at last, we will see how mathematics can be applied in modeling the new pandemic, COVID-19. It is interesting to think about the evolution of mathematics. The notion of mathematics is nearly as old as humanity itself. It has evolved from simple counting, measurement, and calculation. Then it developed through application of imagination and logic to the abstract discipline we know today. The world will agree that mathematics has been fundamental to all present day advances in science, engineering, and technology. The evolution of mathematics may be clocked with the origin of numbers. As civilization advanced, numbers advanced with it, and vice versa. The first solid evidence of the existence of the number 1 appears about 20,000 years ago. It was just a series of unified lines cut into a bone, which was called the Ishango bone. The Ishango bone is a bone tool and possible mathematical object dated to the Upper Paleolithic era used to perform simple mathematical procedures. Numbers and counting began about 4000 BC in Sumeria, one of the earliest civilizations. The method of counting began as a series of tokens. Each token a man held represented something tangible, say 5 chickens. If a man had 5 chickens, he was given 5 tokens. When he traded or killed one of his chickens, one of his tokens were removed. This was a big step in the history of numbers and counting because with this step, subtraction and thus the invention of arithmetic was invented. Under the curious minds of the ancient Greeks, beginning with Pythagoras, mathematics rose to a highly evolved level of theoretical mathematics, which ushered in a golden age of maths. Next came the Romans, and they did all their calculating on a counting board, which was an early version of an abacus. The next big advance in the world of numbers and mathematics came around 500 AD in India, that is the invention of zero. Once zero was invented, it transformed counting and mathematics in a way that would change the world. Zero is still considered as India's greatest contribution to the world. For the first time in human history, the concept of nothing had a number. The next big advance in numbers is the invention of fractions that came in 762 AD, that is in Persia. By 1200 AD, Arabic numerals made their way to North Africa and from there to Europe. Later, Leonardo Pisano Bigelow who would later be known as Fibonacci, had been raised using Roman numerals. The next big evolution in numbers came in Germany in 1679, when the German mathematician Leibniz invented a system of counting that used only ones and zeros, what would eventually be called the binary system. In the binary system, ones stand for something and zeros stand for nothing. Leibniz even went so far as to design a machine that would count in binary. Though he designed this binary machine, he never built it, and the world would have to wait another 265 years before this one and zero usher in the modern world. The machine designed by Leibniz was built in 1944 during the Second World War in England as a code-breaking apparatus. From there, the binary system was adopted and used in every computer ever built. Computer code has literally made possible the internet, space exploration, and indeed our modern life. Thus, it is very much interesting to explore the evolution of numbers, which is fundamental in the progress of mathematics. However, I take you to see some general applications of mathematics. It has applications in almost all fields: science, technology, business, medicine, meteorology, astronomy, etc. From elementary addition and subtraction to rocket science, mathematics is present everywhere. Just as an architect might create a cardboard model of a structure being designed in order to understand it better, scientists use mathematical models to understand and solve real-life problems. They use differential equations, difference equations, integral equations, calculus in general, statistical methods, sequence and series, topology, fuzzy mathematical tools, graph theory, operation research, etc. That is, whatever you studied under the subject mathematics is being used to create mathematical models. Let us see some applications. First one, satellite navigation. To determine any location on Earth, satellite navigation systems like GPS use signals from satellites which provide extremely accurate times. Scientists use the idea of metric space in satellite navigation. A metric space is the mathematical generalization of measuring distances. Because of general relativity, GPS receivers use the curve metric rather than the usual Euclidean metric. Second one, weather prediction. The weather is an incredibly complex system with billions of molecules interacting. This makes predicting the weather a surprisingly difficult task, even using the extensive network of weather stations, satellites, and the world's largest supercomputers. Fluids like the atmosphere follow a set of rules called the Navier-Stokes equations. Navier-Stokes equation is a partial differential equation that describes the flow of incompressible fluids. The equation is a generalization of the equation devised by the Swiss mathematician Euler in the 18th century to describe the flow of incompressible and frictionless fluids. Supercomputers
divide the entire atmosphere into millions of blocks, each around 1 cubic kilometer in size, and use numeric simulations to create a high resolution forecast. Only the accuracy of mathematical models and speed of computers can provide reliable outputs. Next is population dynamics. Quantification is an important element in population studies as population data are available in a discrete quantifiable form. The relationship of population studies with mathematics therefore assumes great importance. The study of population size, growth, structure, and components is entirely done with the help of mathematics. Population experts have attempted to build various mathematical models regarding population growth. Mathematics is thus an important tool in the study and understanding of population phenomena. Next is about constructions. One of the many professionals involved in construction is structural engineers. Structural engineers turn architectural design into reality. They use several areas of mathematics to assess how structures react to forces in the environments. For example, structural engineers consider how the vibrations created changes in the structure. Wind, underground transportation, earth movements, walking, or vehicles all cause vibrations. They highly depend on mathematical models and equations for finding the correct solutions for their problems. When suspension bridges are constructed, they are actually quite flexible to prevent buckling. This flexibility causes also means these bridges are susceptible to resonance. Resonance is a phenomenon modeled using second order differential equations. Next is about air transportation. Every day there are around 50,000 commercial airline flights. All planes, all luggage, every crew, and all passengers have to be at the right place at the right time, and planes need to be serviced and refueled. Most importantly, planes can crash when arriving at any of the busy airports. This is an incredibly complex logistic challenge, impossible without mathematics and operations systems. In addition, airlines want to save money by creating a more efficient network in which planes take the best possible routes and in which planes are never idle, empty, or out of service. This can be done using algorithms from graph theory. Next application is in traffic optimization. Transportation engineers design transportation systems. They use data analysis to identify problems with the traffic flow. As in air transportation management, they use operation research techniques and graph theoretical models to reduce traffic jams and optimize traffic flow. Next is about finance and banking. In financial mathematics, traders can buy or sell stocks in a company commodity like oil and gold, or derivatives which are virtual goods whose prices are derived from the change of other things. For example, you can buy options which would allow you to buy or sell a stock at a particular price at some point in the future if you still want to at that time. Financial analysts have many different mathematical tools to help them make better decisions. For example, statistical models to analyze historic economic data, or probability and stochastic calculus to predict the behavior of financial markets. Particularly famous is the Black-Scholes equation, which is a partial differential equation used to find the correct value of the derivatives. Next is about image compression. Digital photography started in 1975 with the Eastman Kodak petapixel camera. When we look at images from even 5 years ago, they look different than today. We often refer to lower quality photos as pixelated. This look actually has to do with how digital images are compressed. Mathematical principles are highly used in this area. The mathematics behind it is complex, but the idea is relatively simple. Next application is in speech recognition. Speech recognition is an interesting and difficult problem. Each language has its own set of vocabulary, grammar, and pronunciation. Even within a language, people use it differently. Computers can detect sounds. They use complex statistical models to guess what the sounds mean. The theory of probability plays a vital role in speech recognition. Next is about supply chains. Each time we buy something from a store or order something online or send a letter, we are engaging with a complex system called a supply chain. Our purchases depend on of manufacturing, shipping, stocking, pricing, and sales working together. Supply chains use many different areas of mathematics to combine logistics and finances. Financial engineering, graph theory, and operations research are the three major areas in mathematics which are much involved in supply chains. Next is about internet and phones. Both internet and phone lines form a gigantic network which allows users to exchange data, whether websites or calls. All users are connected by countless links which have a certain capacity. When you make a phone call or request a website, network operators have to find a way to connect sender and receiver without exceeding the capacity of any individual link. Without mathematics of queuing theory, it would be impossible to guarantee a reliable service. Mathematical models using Poisson processes all but guarantee that you will hear a dial tone when making a phone call. Researchers believe that the mathematics of fractals can help create a much more reliable internet service in the future. Next is about computers. It is important to note that computers started to operate after advances in mathematics and logics. A computer usually performs processes. The mathematical foundation of computers is logic. Other fields like linear algebra, calculus, probability, and set theory are mathematical fields which are also applied in computer programs. People with a good understanding of mathematical concepts easily understand how logic controllers work, how to write better algorithms, and how encryption works. Next is in communication network. The rapid
developments in information technology have primarily been possible because of the introduction of network. For a mathematical analysis of transmission, the first necessity is to find out some means whereby the transmitted signal can be coded and expressed in mathematical terms. In other words, a mathematical model must be formulated for the analysis of data communications. Next is about search engines. Billions of people use the internet every day. One of the reasons is that the internet makes it so easy to find information quickly using search engines like Google. In order to find the most useful websites in display them at the top, Google represents all pages on the internet in a gigantic matrix. The matrix knows about how the various websites are linked, and you can use linear algebra, probability, and graph theory to find the most popular sites. Google uses mathematics for many other of its services, finding directions in maps, spam detection in Gmail, voice recognition on Android text recognition, etc. Next is about data analysis. Data is everywhere around us, and new data is created every time we browse the internet or complete a survey or go shopping. Scientists collect data whenever they conduct an experiment, and sometimes these data sets are so large that they need to invent entirely new technologies like the internet to process them. To make sense of data, we need statistics. Using mathematics, we can convert a large collection of numbers into very accurate information about the system which created the data. Statistics can also tell us if certain findings are valid or significant. Next is about ATM security. ATMs originally used a mathematical formula or algorithm known as the data encryption standard to encrypt personal identification numbers. The data encryption standard encrypts data in 64-bit blocks using a 56-bit encryption key. Since digital communication has become so universal, the National Institute of Standards and Technology developed the Advanced Encryption Standard to safeguard information. This specification dictates a complex encryption algorithm that can use cipher keys of different lengths of 128-bit, 192-bit, or 256-bit. Next is about artificial intelligence. The primary purpose of artificial intelligence is to create an acceptable model for human understanding. And these models can be prepared with the ideas and strategies from various branches of mathematics. Artificial intelligence is just mathematics. The ideas behind thinking machines and the possibility to mimic human behavior are done with the help of mathematical concepts. Artificial intelligence and mathematics are the two branches of the same tree. The concepts of linear algebra, calculus, game theory, probability theory, statistics, advanced logistic regressions, and gradient descent are all major data science underpinnings. Then, about movie graphics. While any form of experimental or abstract animation can be called motion graphics, the term typically more explicitly refers to the commercial application of animation and effects to video film, TV, and interactive applications. The ideas of linear algebra are used throughout movie graphics. Knowledge of calculus is an important part of advanced movie graphics. Differential geometry, which studies equations that govern the geometry of smooth curves and surfaces, is also used in graphics. A thorough knowledge of computational geometry, which is the study of efficient ways to represent and manipulate geometry within the computer, is also essential in developing the theory of movie graphics. Movie graphics put the mathematics and art of digital images in motion. They rely on high-level mathematical concepts to simulate familiar visual, auditory, and movement patterns. Movie graphics often incorporate vector spaces in 3 dimensions. Next is about robotics. A robot is a machine capable of carrying out a complex series of actions automatically. Robots may be constructed on the lines of human form, but most robots are machines designed to perform a task with no regard to their aesthetics. The branch of technology that deals with the design, construction, operation, and application of robots, as well as computer systems for the control, sensory feedback, and information processing, is called robotics. Robotics is the intersection of science, engineering, and technology. The fundamental mathematical areas used in robotics are calculus, ordinary differential equations, advanced linear algebra, geometry, and numerical analysis. Mathematics is even used in cooking, that is, in microwave ovens. Microwave ovens work by exciting the water molecules in rather cooking from the outside in light stoves and ovens. Microwaves cook from the inside out on a molecular level. In microwave heating, modeling can be a design tool to understand and develop optimum heating procedures. In the modeling process, the food system is broken down into many small elements. Simulation of the source of microwave is possible and solution to the electric field equations can be obtained. Many different areas of mathematics, like differential equations, work together when describing the forces behind the microwave oven. These are instances of only some of the applications of mathematics in our daily life. Now, let us see some applications of mathematics in medical field. The history of mathematics in medical sciences can be traced back at least to 1798 when Thomas Malthus, an English cleric and the well-known economist, published his famous gross law of the human population. Mathematics plays a crucial role in medicine, and because people's lives are involved, it is very important for nurses and doctors to be very accurate in their mathematical calculations. Medical professionals use math when drawing up statistical graphs of epidemics or success rates of treatments. Nowadays, mathematics is being successfully applied to a number of important fields in medicine, including biopool, cardiovascular diseases, clinical schedules and tests, data analysis, drug design and discovery, epidemiology, genetics, image processing, immunology, instrumentation, microbiology, neuroscience, oncology, virology, and many more. In medical imaging, mathematics is used extensively. One of the more advanced ways that medical professionals use mathematics is in the use of CAT scans. A CAT scan is a special type of X-ray called a computerized axial tomography scan. In CAT scans, MRIs, and similar diagnostic technologies, images are made from thousands, even millions of different perspectives, and mathematics is used to integrate the information from all these perspectives into a single three-dimensional digital image. We use mathematical tools to study and develop tools and diagnostic procedures in medical science. The most popular mathematical tools we use in medical science are difference equations, discrete time dynamical systems, information theory, coding theory, graph and network theory, integral transforms, numerical and computational mathematics, ordinary differential equations and continuous time dynamical systems, partial differential equations, stochastic and time delay differential equations, statistics, probability and time series analysis. Another device used by medical scientists by the help of mathematics are mathematical formulation of disease models, which are very effective to understand epidemiological prototypes of diseases. It will help us to take necessary measures of public health interventions by controlling the spread of the diseases. Increasingly, scientists are calling on mathematicians to help them to understand the spread of disease or the mechanisms of disease by the creation of mathematical model of the population. The mathematical models used in epidemiology or in creating treatments of diseases like the severe acute respiratory syndrome, commonly called the SARS, or the human immunodeficiency virus, commonly called HIV, or cancer, or Parkinson's disease, are often either differential equations models, or matrix models, or models from discrete mathematics. Moreover, they often must incorporate statistical tools into the models because biological processes are rarely deterministic. These models are used to predict the way the real situations develop and then used to understand how to modify those outcomes. For example, I'll tell you some of the mathematical equations we use in medical science. One is the Radon transformations. Radon transformation is a complicated integral equation combined with Fourier transformations used in MRI scans and ultrasound. Maxwell equations is another one. It is a set of equations widely used as a well-known diagnostic tool across a range of medical applications. It is used in cancer therapy of hypothermia. Another important mathematical equation used in medical science is the Navier-Stokes equations. These equations are widely used in biomedical engineering and medicine. Another application of mathematics to medicine involves a lithotripsy. This is a medical device that uses a property of an ellipse to treat gallstones and kidney stones. Lastly, let us see how mathematics may be used in the present scenario of COVID-19. We are fully aware of the pandemonium and chaos created by this monstrous disease. Among us, some may have been infected by the virus. Some may be mourning on the demise of the dear ones through it. Anyway, the sense of fear caused by this pandemic is universal. Above all, we all are affected by the economic slowdown in all areas of economic activity. People all over the world are anxiously asking when will this come to an end. When a new epidemic starts, one may fear that it will not stop since there are always new cases. This is not what mathematics is. The important quantity is the reproductive ratio, that's R0, which corresponds to the mean number of individuals infected by each infectious disease. If R0 is less than 1, then the epidemic dies, while it spreads if R0 greater than. The knowledge of R0 guides the strategy to control the epidemic. In particular, in case of limited resources, for instance, not enough vaccines for everyone, the goal is to use these resources to decrease R0 below 1. Let us see the chronology of COVID-19. In early December 2019, the public of Wuhan, Hubei province of China, are infected by an unknown pneumonia infection. This pneumonia has been caused by novel coronavirus, which is officially named by WHO as COVID-19. According to medical records, coronavirus was first identified in 1965, and after that, 3 vital outbursts happened. In 2003, the first outbreak occurred in mainland China, named as severe acute respiratory syndrome, commonly called SARS. The second outburst happened in 2012 at Saudi Arabia, known as Middle East Respiratory Syndrome, commonly known as MERS. Third outburst was occurred in South Korea in 2015. And the present one was the fourth outburst and is occurred in the form of COVID-19 in China and spread globally. Now, it has turned out to be a pandemic outburst in 205 countries. Since the COVID-19 virus is transformed from human to human, the country, particularly India, with a high population density, is in an alarming situation. If proper strategy or measures cannot be taken to protect the spreading of COVID-19 virus, it will cause deaths of many more Indians. Now, not only medical and biological research, but also mathematical modeling approach also cooperates and plays a crucial role to stop COVID-19 outburst. By By mathematical modeling, we may forecast the point of infection and finishing time of the disease. It also helps us to make proper decisions about the necessary steps to restrain the spreading of the disease. Again, mathematical modeling supported by the dynamical equations can afford detailed characteristics of the epidemic dynamics. At the early stage of COVID-19 pandemic, many researches have been done in statistical approach as well as in mathematical modeling to guess the main endemic parameters such as reproduction number, serial interval, and doubling time. Several researchers have already devised mathematical models for studying the spread of COVID-19. Some were used fuzzy mathematics for modeling. Here, I present a model by a team of 4 researchers, namely D. Pal and G.S. Mahapatra from Westminster, D. Ghosh from NIT Puducherry, and P.K. Sandra from Calcutta. They claim the model will be fitted in Indian situation. In this model, they divided Indian population N into 5 subpopulations such as susceptible population S, infected but not detected by testing population E, quarantined population Q, confirmed infected population who are under treatment in isolation ward I, and the population who are lived in secured zone not affected by COVID-19 virus R. They identified 11 parameters as follows. The recruitment rate at which new individuals enter in the Indian population are lambda. The transmission rate from susceptible population to infected but not detected by testing population as alpha. The transmission coefficient from susceptible population to quarantine population as beta 1. The transmission coefficient from infected but not detected by testing population to quarantine population as beta 2. The transmission rate from susceptible population to secured zone population as sigma 1. The transmission coefficient from infected but not detected by testing population to secured zone population as sigma 2. The transmission rate from quarantine population to secured zone population as sigma 3. The transmission rate from infected but not detected by testing population to infected population for treatment as R1. The transmission rate from quarantine population to infected population for treatment as R2. Death rate of infected population due to COVID-19 infection as D2. And the natural death rate of all 5 subpopulations as D1. In the SEQIR model, several demographic effects are included by supposing a proportional natural death rate D1 in each of the 5 Indian subpopulations. Differential equations for susceptible population S is ds by dt equal to lambda minus alpha SE minus beta 1 S minus sigma 1 S minus D1S. Differential equation for infected but not detected by testing population E is d by dt equal to alpha SE minus R1E minus beta 2E minus D1E. Differential equation for quarantine population Q is dq by dt equal to beta 1s plus beta 2e minus r2q minus sigma 2q minus d1q. Differential equation for confirmed infected population I is di by dt equal to r1e plus r2q minus sigma 3i minus d1i minus d2i. And the differential equation for secured zone population not affected as R is dr by dt equal to sigma 1s plus sigma 2q plus sigma 3i minus d1r. Using dynamical modeling analysis, this model can forecast the confirmed COVID-19 cases in future, specifically in different states in India. This model can also analyze the transmission dynamics of the COVID-19 virus amongst humans. Let me wind up this discourse here. Once again, I thank the organizers of this international conference, especially Dr. Rita, for inviting me to this wonderful event. I also take this opportunity to thank all the participants for your kind attention to this talk. May God bless you all. Thank you.
Thank you, madam, for your nice presentation.
Dear principal,
Participants, if you have any queries, kindly post your question in the chat box. Thank you, madam, for your nice and wonderful presentation. I want one clarification, ma'am.
Yes.
How is lithoproider is used in the medical field for diagnosis?
I think it is used for detecting the stones in gallbladder and like that. I'm not a medical doctor, so I'm not aware of it's a deep thing.
It is a new word, ma'am, so that I want to.
Okay.
The fuzzy mathematical model, has it been applied to this COVID-19 cases to identify?
Yes. It is used. The pure, both pure mathematics and applied mathematics, both are used. Also, these types of tools from fuzzy mathematics, not from the, not even from the regular fuzzy. It is from all types of fuzzy, like rough or soft or illusionistic. All are used.
One participant, Keshav Kumar, is asking this question, ma'am. I think people with diabetes and respiratory problems are more prone to spread of COVID-19.
Yes. Yes, it is.
Yes.
Medically, it is correct. It is not from the mathematical part. Medically, it is correct. That's it.
Yes.
We are only making the models, how far it will go and how can we make a stop for it, like that. about the spread, all that.
Nice explanation, ma'am. He himself asked another question, Keshav Kumar.
Yes.
Your
Yes, ma'am.
model does not describe this special case.
The respiratory problems.
Yes, ma'am.
Many types of models are there. I have taken one model, and I think it used more mathematics, so I have presented that. It is not my model. I told it. It is from 4 scientists from various parts of India.
Thank you, ma'am.
Yeah. Right.
So first of all, I thank you, ma'am, for joining with us and spending your valuable time with us. Also, thank you so much, ma'am, for your crystal clear explanation on the applications of mathematics in the various fields.
Yeah.
Your explanation of mathematical models in the field of medicine is excellent, ma'am. Moreover, lastly, your presentation on the role of mathematics in the present scenario of COVID-19 is highly beneficial to the society to overcome this pandemic situation. So once again, I thank you so much, ma'am.
Okay, Vinanda, I thank Rita, also Rita, my friend, and her team for the excellent conducting of the conference. I wish you all the best.
Thank you, ma'am. Thank you so much.
Let's take a break from 12 p.m. to 1 p.m. The event will commence sharp at 2 p.m. I repeat, let's take a break from 12 p.m. to 2 p.m. The event will commence sharp at 2 p.m.
Today, paper presentation session starts at 2 p.m. Today's paper presentation session starts at 2 p.m. Paper presenters are asked to join 15 minutes earlier to the session. Thank you.